Okay, so this is not what we want. This is actually something that is weaker than the statement number 2. It seems that dropping u in the statement 2 is not very realistic. However, we might want to simplify the statement 2 by changing it to a statement that is stronger than it. And here's a possible choice. Let me write it down as a remark number C. We consider the following statement, that AT applied to the set of non-zero integer vectors in Zm. Remember, A is n by n matrix, so AT will be an n by m matrix. The statement is that this set has empty intersection with Zn. And now let us compare this with our statement number 2 in Kronecker's theorem. And we claim that this guy is stronger than the statement 2. So we have this implication, but not the other way around. The forward direction is kind of vacuous. This is because for any u in Zm, there will be two possibilities. If u is 0, then automatically you have ut times b is 0. So this is true. If u is not 0, then by our hypothesis, ATU is not an integer vector in Zn by our hypothesis. So it follows that this part, the hypothesis of the statement we want to prove, is false. So the statement itself, that this implies this, is true by logic. And this proves our forward implication. For the backward implication, which is false, we can use the following example. You consider a case when m is equal to 2 and n is equal to 1. And you let A to be the 2 by 1 matrix with 2 entries, 1/2 and 1. And you take B to be just a 0 vector. Then ut times b, which is 0, is always an integer. So the statement 2 is always true, because this part is always true in this situation. So 2 is always true. But this guy will fail. This is because AT in this situation is the 1 by 2 matrix with 2 entries, 1/2 and 1. And if you consider AT times the column vector 2, negative 1. What do you get? You will get 0, which is in Zn, which is Z1, because here n is 1. And this vector is non-zero. So you get AT applied to Z2 minus 0 intersection Z1 is non-empty. And this tells you that the left-hand side fails. So what we got is a statement that is strictly stronger than the statement 2 in the Kronecker's theorem. It shouldn't be hard for you to realize that those two guys are not equivalent, because we are ignoring the vector b in this statement. At this point, some of you may have an immediate question. Why are we using AT here instead of A itself? Can we replace this AT by just A and swap integer m and integer n, as we did for this asymptotic version of Dirichlet's Diophantine approximation? Remember, this condition really just means that A of Zn minus 0 intersection Zm is empty. This is the same as this sentence. Why in the inhomogeneous setting we have to use AT instead of A, like in here? As a matter of fact, for the homogeneous setting, if there's no B, then the first statement of the Kronecker's theorem immediately follows from here. So if there's no B, we can use this as a hypothesis for the Diophantine approximation. However, if there's indeed an B, then there will be some subtleties in here, which I will explain in our next remark. So our next remark will be called the remark D. So I want to tell you that this condition unlike this does not imply the second statement of the Kronecker's theorem on inhomogeneous Diophantine approximation. Let me first explain to you why this statement is not equivalent to this statement that uses AT. So this is not equivalent to AT applied to Zm minus 0 intersection Zn equal to empty. As an example, you consider the following. Let m equal to 2 and n equal to 1, and you take A to be a 2 by 1 matrix with square root 2 and 1 as entries. Then A times any non-zero integer is impossible to be an integer vector. And this tells you the left-hand side holds, but the right-hand side fails. This is because if you consider AT, this is AT, and you multiply by this vector, this gives you just 1, which is an integer. So this tells you right hand side fails. So they are not equivalent. Symmetrically, you can always produce a mirror example that shows right hand side holds but left hand side fails. Remember that previously we had this statement, this guy implies the second statement of the Kronecker theorem. But now I will tell you that this statement with A instead of AT does not necessarily imply this guy. So this does not imply this guy. We'll still use the same example as above. M equal to 2 and N equal to 1. And A is a 2 by 1 matrix, square root of 2 and 1. And you take B to be the vector 1/3, 1/3. Now take U to be the vector 0, 1. In Z2, it follows that ATU is 0, which is an integer. But UTB, what is UTB? This is equal to 1/3, is not an integer. So this statement fails. But as we have shown in here, the left hand side holds in this example. Because the second statement in the Kronecker theorem fails. And by the Kronecker theorem, this guy is equivalent to the first statement, which says the pair A and B can be approximated by integer vectors sufficiently well. So in particular, this tells you that this condition does not necessarily guarantee a good approximation in the inhomogeneous setting. Remember, this is equivalent to the system 1. The inhomogeneous diaphantic approximation. And this justifies this in some sense that we better use this AT assumption instead of the assumption that involves A rather than AT. And that is all the remarks that I would like to make at this moment. So now let's start the proof.